Welcome to this third presentation about electrophilic alkylations of carbon nucleophiles. This video is about the alpha alkylation of ketones. In other presentations, I already explained how ketones can be prepared from acyl halides or from secondary alcohols, and many different, structurally diverse ketones are therefore readily available. Most ketones are stable compounds that can be used as solvents or fragrances, but the reactivity as electrophiles or nucleophiles is still sufficient to make ketones useful synthetic intermediates. In this presentation, we'll have a look at the use of ketones as nucleophiles. Although strong electrophiles may even alkylate ketones in the absence of any base, it is usually the more nucleophilic ketone enolates that are alkylated. These are formed by deprotonation of ketones with catalytic or stoichiometric amounts of base. Because ketones are weak acids only, stoichiometric enolate formation requires strong bases, such as sodium amide, LDA, or potassium terts butoxide. Ketone enolates are ambident nucleophiles and can be alkylated either at carbon or at oxygen. Hard electrophiles, such as sulfonates, alkyl chlorides, or trialkyl oxonium salts, tend to alkylate at oxygen, whereas softer electrophiles, such as alkyl iodides or electron-deficient alkenes, show a higher tendency to alkylate at carbon. Suitable alkylating reagents include alkyl halides, sulfonates, epoxides, and electron-deficient olefins. Recently, catalysts have been found that can abstract hydride from alcohols or amines reversibly. Such catalysts can bring about formal alpha alkylations of ketones by aldol condensation followed by hydrogenation. For laboratory scale preparations of structurally complex molecules, the scope of this strategy appears by now to be too narrow. But for large-scale preparations of smaller molecules, this strategy can offer some advantages. Let's have a short look at potential alternatives to the alkylation of enolates. Because ketone alkylations do not always proceed smoothly and strong bases and low reaction temperatures are expensive, other strategies may be superior, even if they require more synthetic steps. A very good strategy is aldol condensation followed by hydrogenation. Aldol condensations proceed well with only catalytic amounts of bases or acids, and the only byproduct is water. Sometimes such condensations do not even require a solvent, and hydrogenations are also easy to perform and do not generate any waste. If the target ketone does not contain groups incompatible with hydrogenations, such as other olefins or sulfur, this two-step approach is often the best strategy to alkylate ketones. Some ketone enolates are not nucleophilic enough to react with a given electrophile or undergo self-condensation too quickly. In such instances, it may help to convert the ketone into an imine or hydrazone. Because of the longer nitrogen metal bonds, if compared to oxygen metal bonds, metallated imines do not react with imines as quickly as ketone enolates with ketones, what helps to prevent self-condensation. Then, imines are less acidic and less electrophilic than ketones, and metallated imines therefore more nucleophilic and basic than ketone enolates. This strategy is particularly useful for the alkylation of aldehydes, which are still more acidic and electrophilic than ketones. A third indirect strategy to alkylate ketones is their alpha acylation with an acidifying auxiliary group, for instance a formyl, trifluoroacetyl or alkoxycarbonyl group. The readily available acetoacetates, for example, can be used as synthetic equivalents of acetone. 1,3-dicarbonyl compounds are much more acidic and can be alkylated or olefinated with weaker bases than the starting ketone. After the alkylation reaction, the auxiliary group can be cleaved off again, for instance by treatment with a nucleophile. In a later video of this series, I'll show you more in detail how to alkylate 1,3-dicarbonyl compounds. Further indirect strategies for the alkylation of ketones include the preparation and alkylation of enamines and of silyl-enol ethers. As will be discussed in a later presentation, enamines only react well with strong alkylating reagents, such as benzylic or allylic halides or haloacetic acid derivatives. But at least no strong bases are required. Silyl-enol ethers are weak nucleophiles only and can usually only be alkylated under acidic conditions with carbocations or carbocation-like intermediates. The main advantages of this strategy are the ready availability of a large selection of structurally diverse starting materials and that most enolate alkylations are fast reactions. Moreover, most ketones are stable compounds and easy to handle safely. Disadvantages are that with some electrophiles, such as methyl iodide, multiple alkylations can be difficult to avoid. Also, when attempting to alkylate ketones with only catalytic amounts of base, aldol additions will often compete with the alkylation. A number of other annoying side reactions will be discussed later. In this example, the authors discovered that catalytic amounts of tertiary amines greatly improve the yield and selectivity of the alkylation of ketones with sodium hydroxide as base. Despite the low yield, procedures as this one can be competitive if the target ketone can be purified by distillation, because all the reagents are inexpensive and no low temperature is required. Because of its low solubility, sodium hydride is not well suited for the stoichiometric formation of sodium enolates from simple ketones. In this example, however, a good yield of allylated ketone could be attained, interestingly without allylic inversion. This is a further example of ketone alkylation without the use of low temperature. In this example, the alkylation was intramolecular, and as base, potassium terzbutoxide in terzbutanol THF was used. Surprisingly, no elimination of the tertiary chloride occurred. With alkyl bromides or iodides and bases such as LDA and THF at low temperature, such alkylations often give less byproducts and higher yields. But the high cost of these strong bases restrict their use to expensive starting materials, where these costs are only a negligible fraction of the total expenses. This is an older example of the alkylation of a deprotonated imine. As base, ethyl magnesium bromide was used, and the alkylation was conducted in refluxing THF. Unfortunately, no yield was given, and the regioselectivity of the alkylation was poor. At lower temperature, however, better selectivities can often be attained. Examples have also been reported of the use of enantiomerically pure amines as auxiliary for enantioselective ketone alkylations. This is a recent example of the alkylation of a ketone with an alcohol by intermediate aldol condensation. Most other examples require iridium catalysts and expensive ligands, and the use of nickel is certainly a great improvement. Unfortunately, most examples of the use of aliphatic alcohols for the direct alkylation of ketones only proceed well with benzylic alcohols. These are, of course, easy to oxidize, and the intermediate benzaldehydes do not undergo aldol additions. But it is not clear if the use of benzylic alcohols is superior to the aldol condensation with benzaldehydes followed by hydrogenation. The example on this slide is one of those rare exceptions where an aliphatic non-benzylic alcohol could be used as alkylating reagent. An excess of a strong base was, however, required, and the yield was low. The aldol condensation hydrogenation strategy mentioned earlier is probably more economical and easier to perform. This is an example of such a two-step aldol condensation hydrogenation sequence. The C-C bond forming reaction was run in an excess of acetone, which could be recovered and recycled. The intermediate mixture of secondary alcohol and olefin was hydrogenated in the presence of 0.6% of toluene sulfonic acid to complete the formation of the alkene. Because the starting materials and intermediates were devoid of any catalyst poisoning functional groups, a small amount of palladium was sufficient to catalyze the hydrogenation, which again could be accomplished without any solvent. ketone enolates are usually not nucleophilic enough to add to unactivated olefins. The addition of ketone enolates to styrenes in DMSO has been reported, but the combination of DMSO with strong bases is dangerous and almost impossible to scale up safely. In the presence of peroxides or other oxidants, however, ketones may add to simple olefins or even electron-rich olefins, such as enol ethers, by a radical chain mechanism. In this example, upon heating the peroxide, homolytic cleavage of the oxygen-oxygen bond generates two oxygen-centered radicals which abstract hydrogen atoms from the alpha-methylene group of cyclohexanone. The resulting electron-poor carbon-centered radicals add to the electron-rich alkene to generate an electron-rich alpha-alkoxy radical which again abstracts hydrogen from the ketone. Unfortunately, a large excess of ketone was required, but this could be separated from the product by distillation. This is a further example of radical chain alkylation of cyclohexanone with an unactivated alkene. Instead of a peroxide, oxygen and catalytic amounts of manganese and cobalt salts were used as initiators. One drawback of this strategy is that benzylic and allylic CH bonds are cleaved at a similar rate or faster than alpha CH bonds of ketones, and are therefore incompatible with these conditions. Toluene, for instance, would be oxidized to benzoic acid under the conditions of this example. Anyway, for target ketones devoid of arenes or additional olefins, this strategy can be more convenient than the alkylation of enolates. So, what are the potential side reactions? When using very hard or carbocation-like alkylating reagents, O-alkylation of ketones or their enolates can compete with C-alkylation. Oxygen alkylation also occurs more readily in polar aprotic solvents and with cations that do not bind strongly to oxygen. Thus, sodium or potassium enolates are O-alkylated faster than lithium enolates. In the example on this slide, the potassium enolate of cyclohexanone underwent extensive O-methylation upon treatment with dimethyl sulfate, a notoriously hard electrophile. When alkylating ketones with electron-deficient alkenes, occasionally a second reaction of the ketone with the electrophilic activating group is observed. In this example, for instance, cyclohexanone was alkylated twice by an alpha-beta unsaturated ketone. Such reactions should not occur upon stoichiometric enolate formation, because in the initially formed intermediate the negative charge will be at the activating group, which should therefore no longer be electrophilic. This intermediate may, however, add to the original ketone and yield a cyclobutanol, as shown here. Such formal 2+2 cycloadditions of enolates to electron-deficient olefins do not occur often. With enamines, however, such cyclobutane formation is more prevalent. Further potential side reactions include multiple alkylations of the ketone, destruction of the electrophile by elimination or substitution, and self-condensation of the ketone upon incomplete enolate formation. Some of the common bases may also act as hydride donors and reduce the ketone or the electrophile. Such reactions tend to happen when either the ketone or the electrophile are sterically demanding and the C-C bond forming reaction therefore slow. When using transition metal catalysts, for instance for the direct alkylation with alcohols, also the ketone may be dehydrogenated. This will occur readily if dehydrogenation leads to the formation of arenes or heteroarenes. Finally, some polar aprotic solvents may act as electrophiles or oxidants, for instance DMF and DMSO. These solvents are often used even as additives only because of their ability to dissolve salts and because most reactions proceed much faster in these solvents than in less polar solvents. Strong nucleophiles, electrophiles and bases can, however, react with most polar aprotic solvents and cause the formation of unexpected byproducts. On this and the next slide is a short selection of some more examples which you may find helpful. In the next presentation we'll have a closer look at the alpha alkylation of aldehydes. which is more difficult to perform than the alkylation of ketones. See you there.